Okay, so we are of course here to celebrate TVR, and I'm not quite sure who he's handing this mobile phone to, but I found this very interesting picture on the internet. So I'm from the physics department of IISc, and IISc physics department is actually TVR's child. Right? I think this is not an exaggeration, and I have greatly benefited by being in this department. So how would I describe myself as I have to recall for you a composition of Saint Tyagaraja. So this is a composition in the Raga Mukhari. What he says is, Entanine Varnintunu Shabari Bhagyam. It's in Telugu. So if you know Indian mythology, then Shabari is an old woman, humble, no pedigree, nothing. Yet she is able to, take wild berries, taste them, and give it to Sri Rama. And Sri Rama blesses her for that. So my situation is precisely that. I'm the Shabari here, and he is the Sri Ram, right? So I've been really blessed. I have neither talent nor pedigree, but TVR took me into his lap, and here, thank you, TVR. Okay, so with that statement, I have to acknowledge people who have actually done the work I'm going to talk about. So there is Hiranmay Das. He's a student at IISc. He's a wonderful young person. I've learned a lot from him. In a year or so, he'll be looking for postdocs. So if you don't consider him, then you are making a mistake. All right. The next person, another hero of this story is Soumya Bera. He is a faculty member at IIT Mumbai. The wonderful person. Again, I've learned a lot from him. And his graduate student, Naba, he's also a very, very exciting person to talk to. I think he's now working with Professor Merlin. Okay, I've been funded by now ANRF for many years, so I'm very grateful for that. Okay, so I'm going to talk about something called frozen Dirac fermions. So TVR has made many contributions, and I don't know if people have talked about this, but he actually had a very beautiful paper on freezing, right? But this freezing is not that freezing, right? I wanted to connect with that, but yeah. So what I'll do is I'll divide my talk into, let's say, 3 parts. First, I'll try to tell you a little bit about what TVR has taught us. So I noticed that there are some undergraduate students who have taken my courses, etc. So I thought they'll benefit by actually knowing what the excitement is all about, right? Okay, then I'll tell you a little bit about fermions in Z2 gauge fields. And I have to make one very important statement before I start. The work that I'm going to present is not motivated by any experiment or something. So I read the papers by many people who are in this audience, and we started working on some of the things that were stated in those papers, and we found some interesting stuff, and we just pursued that just purely from trying to understand the physical ideas behind things. Okay, so it's not motivated by experiments. I have to say that. So this may be somewhat at odds with TVR style of doing things. Yeah. Okay, so question I'm going to ask is about what happens to Dirac fermions when there is some kind of Z2 flux disorder. Okay, so let's start from the very basics. So I certainly apologize to experts, and I hope that I'm not going to make any factual errors when I recount the history as I see it. Okay, so let's just discuss how the field of localization and all the excitement that followed started. So Anderson in 1958 wrote this seminal paper which pointed out that if I have, let's say, a tight binding model, and you have some on-site potential disorder with some width W, then he pointed out that if you increase the strength of disorder beyond some critical value, all the states are localized. Localized means they would sort of exponentially localize around some point. Okay, and sorry. When it is in 3D for some very large enough disorder, in any dimension for large enough disorder. Yeah, and so the extended state picture is something that can carry current, it's delocalized and so on. And this localized state looks something like this. Okay, so if W is less than WC, then something interesting happens. You can have both extended and localized states in your system. And Mott presented an argument in the 60s in a series of papers, which pointed out that the energy at which these localized and extended states appear are separated by something called the mobility edge. So all the states in this energy range will be of this kind, and all the states in this energy range will be of this kind. Okay, so this is what was pointed out. And of course, it was checked by numerical calculations, etc. And what one then realized is that if you put your chemical potential in this and fill all the states up to here, you will have a diffusive metal. And if you are here, you will have an Anderson insulator, which is a thermodynamic metal, but a transport insulator. Okay, so this is what was the status at the in this time. So how do we characterize a diffusive metal? You can of course characterize it by the diffusion constant, and if you use the Einstein relation, you can also characterize it by the conductivity, right? So that's the conductivity. And so the question was the following. Suppose I were to tune the chemical potential and go from extended states to localized states, how does the conductivity change? Right? So if you've done my course last semester, some of you did, you may think that this looks like some kind of order parameter, and the order parameter has to vanish or something in some order disorder kind of transition. So if you take that idea into this, the question is, do you get a continuous kind of transition, or do you have something like a sudden jump? So Mott opined that there has to be a sudden jump, because his point was that if the Fermi momentum times the mean free path becomes order 1, then you can't think about like electrons carrying current, and so suddenly it has to get localized, and you would get this. So this was the question that was being debated during those times, and this is where the Gang of Four entered. Okay, so they showed that the transition is continuous, and there is no Mott minimum in 3 dimensions. And this is the famous paper that all of you have seen in this meeting. And so what they showed is that if you have some dimensionless conductance, which is denoted by G here, if G is above certain value in 3 dimension, it will flow off and you will get what is called as an ohmic metal. Right? If G is less than that value, then it will sort of flow off here, and which means that there is some strength of the disorder at which you can have zero. That means it's the continuous kind of transition that I talked. What came out of this is more interesting in the sense the title of this paper is that what they showed was that there are no mobility edges in 2 dimensions for whatever strength of disorder, that all states are localized in 2 dimensions. Okay, and this is what is come to now called as weakly localized. Now this paper, when I read for the first time, I didn't understand anything, to be honest. There were some arguments of Thouless and all that which made sense, but I didn't understand. But I learned what is going on in the system by reading this paper, which Abrams and TVR wrote. And this actually has a very, very nice calculation. I don't know if this paper has been flashed in this meeting so far. So for the students, if you want to understand what weak localization is, I strongly recommend this paper, because it actually shows you like what is going on, computes diffusion constant, and does a very, very physically motivated idea. So thank you for this, TVR. So this was very helpful for me particularly. Okay, so this is for the Shabris in the audience, right, that paper. Okay, so what we can now do is, so there's a theory, we want to test it out in a computer or by some calculation, explicit calculation which makes, let's say, no other approximations. So one way to do this was, these ideas were invented quite a while back in the 70s, 80s. So the idea is called the transfer matrix method. And so the idea is that you have a disordered sample, and the width of the sample is what I'm going to call as M, so this direction. And I have some disorder, and I create some wave packet or some state here, and I see how that state sort of propagates through the sample, right? And you will see that you can write the output state in terms of the input state by something called the transfer matrix. If you now diagonalize a transfer matrix, you will see that it has some eigenvalues. You can write it as a Lyapunov exponent. And if you take the smallest Lyapunov exponent and divide it by this M, you will see that that corresponds to some kind of correlation length. Right? It gives you a length scale. So if you now look at this M by C, this length scale that you pick out, plotted as a function of the width, you can get 3 types of behavior. One is this M by C can go up, which means that the system is localized. what that means is C now has the meaning of a localization length. And C is fixed in the thermodynamic limits. It's the size of it's the length scale of your localized state at some given energy. And then you're increasing the length scale, so it just goes up linearly if you wish. Right? On the other hand, if C is some power of M itself, right, which is what would happen in a delocalized state, then you will see that this M by C will actually die down. So if you are at the mobility edge, then there is no length scale per se. There's no localization length, if you wish, is infinity. And then what you will get is you will get that the C that you get is actually determined by the scale that you have. So you will find that this line is flat. Okay? So this is what you will see. Okay. So what was done is, I mean, many people did this. This is my favorite paper on this. So this McKinnon and Kramer, what they did was they went through this calculation. And their convention is opposite mine. This is why I had to cancel this and write it as C by M. So you see, so I'm plotting M by C here, the C by M. So it will be reversed. So you see that these states are the localized states. These are the delocalized states. And you can see that the delocalized states appear when the disorder strength is small. And the localized state appear when disorder strength is large. And the most important thing to observe here is that there is a particular disorder strength where this will be flat. And those are that is the mobility edge, and that's the critical state in the system. Yeah. What do you mean by how the system behaves at this line? Yeah, yeah. Yes, yes. No. The conductivity of the line in this problem will be 0 because that's where in this problem will be 0 because that's the precise mobility edge, right? Right, that's this point. That is this point. Yeah, here.
What's the meaning of the correlation lines, the delocalized? What's the physical meaning?
So so there you can't give it the sense of some length scale. So it's sort of determined by the system size. So for example, if you take a block state and ask, what is, I'll explain this when I discuss what is called as the inverse participation ratio. So you will see that if you find out like, what is a scale associated with a delocalized state, it will be determined by the system size. And the normalization will determine, so if, for example, if I have n sites, it'll go as 1 by square root n. So that is that's how it comes.
Related by fusion.
Yes, correct. Okay, so this is the statement. Okay, all right. So I'm going to discuss this right now. Okay, so what you can now do is you can try to characterize some statistical properties of these states, and the statistical properties of these states are characterized by this thing called as the inverse participation ratio. So what you do is, imagine that you have solved this problem on the computer in some box with size L. So number of sites will go as L to the D. And you will see that you can define a quantity. Give me any wave function at some energy. You can define this quantity where Q is a parameter that you have. And you will find that there is a quantity called as the inverse participation ratio. Okay. So the way we have defined it, the normalization of the wave function is respected, saying that the IPR at when Q equal to 2, sorry, there should be actually a P. P2 should be 1. And what happens if you disorder average this is you can argue that in the scaling limit, like you go to very long length scales and so on, you will see that this object should scale as L to the power minus tau Q. Okay. So so if I list out a set of tau Qs for you for different values of Q, you are characterizing this wave function at that energy. Okay, some statistical properties of those wave functions. Okay, so if I have a block state, you will see that this tau Q will go as D times Q minus 1. This comes just from the fact that the block state has, the weight of a block state at a site is 1 by square root of number of sites. So it'll just show up from there. And you'll see, you can pull out what is the dimension of this wave function by simply taking the derivative of tau Q with respect to Q. That will give you in what is the dimension of the wave function. Okay, and if I have a fully localized state, say for example, I delta function localize it at a site, then you will see that this tau Q is just 0 because it will not depend on any length scale. So it will be 0. Okay, so that's the idea. So there are some very interesting properties you can derive for this tau q. Yeah. It can be any number. Yeah. Okay. Tau q, the derivative of tau q has to be positive. Second derivative of tau q has to be negative. These are all properties they're called Holder inequalities. Okay, you can derive them. So generically, you will find that D sometimes is not the space dimension. So if tau q is still linear in Q, whatever coefficient shows up here, that is called the fractal dimension of the wave function. Now, most Anderson localized states have multifractal properties. What that means is that this tau q is not a linear function of Q. And then you can classify tau q into 3 types, as is done in this very nice review article by Evers and Merlin. This is called non-singular behavior. So tau q is not linear, but it does something benign. Then there's something called termination, where tau q does this, and then it goes to a finite value, non-zero value, and it stays there. And this is called freezing multifractality. So this is morally a localized state, but not quite localized, because the small q behavior is different from a fully localized state. Okay, so this is what we mean by freezing. Okay, this is the meaning of the freezing in our picture. Okay, just after the Gang of 4 paper appeared, Wegener sort of wanted to view this actually as a problem in phase transition or something like this. So what he did was he used field theory to describe the same transition that the Gang of 4 had found. And what was pointed out that you can write some replicated theory to integrate out the disorder, etc. And you'll get some soft modes, which are like particle hole excitations of this system. And you can write down a theory for those soft modes. And this turns out to be a nonlinear sigma model with some target manifold, which for the problem where t square equal to +1 is this particular one. And you can write down the RG for this, and you will find that this is the RG equation, and this is exactly what was derived by Gang of 4. And it will reproduce the same set of results that was derived by the Gang. Okay, so this means that what this RG results will show is that 2D systems are always localized. By the way, this is also true in the unitary ensemble, which you can break time result symmetry, still it will be localized. Okay.
Why the RG is only one RG? The conducting will depend on the many parameters of it.
Sure, I mean.
So I saw the Gang of 4 paper since long time this question back up.
Right. So the question is, can you characterize this whole thing by a single dimensionless conductance parameter, right? So the argument is that in certain limit, you can, right? So if you look at very long wavelengths and so on, you can think of this using a single parameter. We can discuss this offline, unless you want to discuss with them right now. Okay. All right. So what we need to do is we have to make 2D great again, because everything is localized in 2D. Or you could, now there is a new thing, 2D first. You have to choose which one you want. You're going to make great again or 2D first. Okay. So it turns out that there is a way to avoid this localization. And that idea comes from introducing additional symmetries in the system, right? So these additional symmetries that you need are not like some space symmetries, they're intrinsic symmetries of the fermions, right? So these are called chiral symmetries. And what was pointed out very soon, okay, maybe 10 years afterwards by Gade and Wegener is that if you have chiral symmetry, you can evade localization. I'll briefly tell you how that happens. So chiral symmetry is realized in many systems which have like particle hole symmetry. We have a symmetric band and you put the energy at the zero. Chemical potential at zero energy, then you can actually realize this. So it's not just a mathematical construct. So what Gade Wegener pointed out is that the target manifold of this nonlinear sigma model, the target manifolds will have something like the elements will be of something like U, the unitary matrices. So here the unitary matrices have an overall phase, right? In addition to like all the other generators of the unitary group, there is an element whose trace is non-zero. So it will produce an overall phase for this matrix. So what happens is if you have that overall phases, even if you start with this term and do RG, you will generate extra terms which actually look at that phase. Okay. So what now happens morally is that you have a problem where you have this matrix sigma model, which is quote unquote also talking to some U1 like object, which is like the face, right? Now you know that if you take a simple U1, something like del phi square, and try to do it in 2 dimensions, you will know that unless you put in some topological defects or something, it will be in some critical phase with some algebraic correlations, etc. So what that means is that you will find that a certain constant coupling to that phase term will not flow, right? And this is in the replica limit with replica number n. If you set n equal to 0, this will force that d sigma by dl is 0. So it will tell you now that if I have chiral symmetry, my conductivity will not flow. This is the state. Yeah.
Simpler, if you just put spin orbit scattering, you can just turn around.
Sure, but I want time reversal symmetry.
Okay. You don't need all this.
Sure, fair enough. If you, yeah.
Non-linear sigma.
Sure. No, if you put non-linear, but that comes from a different physics.
Yeah,
so,
I understand.
Yeah, but this is
localization.
Evading localization 2D, being in the great world of time reversal symmetry. Right? I want to keep time reversal symmetry because that's what I want to use for my Z2 problem. So I need to hold on to time reversal symmetry. Yes, okay, so what Mohit just pointed out is that if I said that to 2D everything is localized for unitary and orthogonal. If I go to the symplectic ensemble, actually it anti-localizes in 2D. Yeah, sorry. I mean, I want t square equal to +1 is what I meant.
Okay.
Sorry. Yeah. Okay. All right. I did say that in the previous. Yeah. What I mean is okay. All right. Okay. So now let me just continue with this. So what these Garde showed is that you will have this conductivity not vanishing, and they also derived a very beautiful result which showed that the density of states will have a divergence at 0 energy. And their original derivation had a factor of 1/2 here, an exponent of 1/2 here. And Montanich, Damle, and Hughes, they actually gave a beautiful argument to show that it has to be 2/3 and so on. And what makes 2D great again is graphene, right? So, 2D belonged to this quantum Hall people, all the field theory types and all, like tight binding people like us, we didn't have much to do there. So graphene gave us a chance to get into, make great common people can do stuff. Okay, so there was vacancies in graphene. So graphene, as you all know, is some honeycomb lattice. And so if you put vacancies in graphene, you will realize that you are going to have Dirac fermions moving in a background with these vacancy potentials. And that will preserve BD1 symmetry. And this is actually Somya's work. So they showed that there is freezing multifractality there. And Kedar and collaborators were able to show that there is this Garde-Wegener singularity. So this results of this theory are kind of, how much time do I have? Okay. All right. So you get this freezing multifractality and this Garde-Wegener singularity. Okay. So the question is, can we look at some of these questions in some other systems? So this is where I'm going to start my discussion of fermions and Z2 gauge fields in 2D. So I'm just going to flash a set of results or set of papers that I have read, which kind of inspired me to look at some of these problems. It's certainly not an exhaustive list of people who have worked on this problem. It's mainly focused on things that I used in my own work. So the first place where you will see fermions talking to Z2 gauge fields is the Kitaev honeycomb model. So this is a spin model. I'm not going to go into the details of it. So this is like some spin-spin interaction with X terms, Y terms, Z terms. That problem can be mapped to a set of Majorana fermions moving in these gauge fields, which are Z2 gauge fields on this link. So if you look at this ground state of this problem, for some nice values of J's, etc., you will see that each plaquette, each honeycomb plaquette will have +1 flux, which means that if a Majorana fermion goes around this, it will not pick up a plus or it will not pick up any sign. The phase for Majorana fermion is a real fermion, so it has only be plus and minus 1. So it will not pick up any phase, and that's what it is. But you can have excited states. These are particularly important for explaining or understanding experiments on these Kitaev systems at high temperatures. You can have these flux defects pop out of vacuum. And then you will have some of these plaquettes to have -1 values. Okay, and those can be random, and there can be a thermal ensemble of them, and God knows what. Okay, so that's a problem where fermions will see this kind of Z2 flux disorder. Okay, so this is what I just mentioned. Okay, so there are some papers that address this. Okay, so there is another context in which a lot of work has been done where Z2 gauge structure emerges. And this is the class of things called orthogonal metals. Rahul and Senthil, many people have worked on these things. And the main set of papers that inspired me. So one of them is one of the authors of the papers here. So Mohit and collaborators, they actually looked at a very interesting problem of coupling fermions to gauge fields in the honest to God way. So put it on the computer, solve it, etc. And this is the phase diagram they got. I will explain a couple of things here. So T is the kinetic energy of the fermions. J is something like the magnetic energy associated with plaquettes. And H is the electric energy associated with the electric field. So don't worry about this H axis. Let's just go along this axis. So what's happening is that I have this gauge theory where there are plaquettes that can be plus or minus 1. And there's an energy associated with that. And T is the kinetic energy. So if you increase the strength of the kinetic energy, at some point, there is a T critical here where you will go from some large Fermi surface to a set of Dirac cones. So spontaneously, the gauge theory will decide that, okay, it's better to have negative fluxes in each plaquette, right? And then it will minimize the kinetic energy of the electrons, of the fermions. So we looked at this region, and what was reported in Mohit's paper was that there is a first order transition. So when we looked at it carefully, we realized that if you go very close to that and try to, instead of putting uniform flux, if you put some slightly flux in different patterns, etc., you can actually minimize further energy. So this transition going from this uniform zero flux phase to the pi flux phase is probably, there are many intermediate phases. And this very same observation was also made by Pierce, I don't know if he's in the audience, in this paper. And they also worked on the same problem. Their problem was much more, somewhat different in the sense that they coupled with the toric code. And they also realized that there can be many different states of different fluxes, which are very, very, very close in energy. So we started by thinking that maybe there is some kind of flux liquid here or some random flux configurations, which could be some going from this phase to that phase. Okay, so this is what led us to thinking about this. And then we solved we just did some tight binding calculations and we looked at it, and then we found that the states are having funny statistical properties. And that is what led to this project. Okay. All right, so I'm now going to talk about fermions in this Z2 flux disorder. So what is the question we are asking? Question is the following. I have a clean system in which there is pi flux through every plaquette. Now what I'm going to do is, I'm going to remove the pi flux and make it zero flux randomly. So this is what I call a flux defect. Okay? And the question is, what is the fate of fermions at zero energy? If I'm away from zero energy, then of course everything is localized, there's no doubt. Right? But what is the fate at zero energy? There I have this T square equal to +1 BD1 symmetry. The question is, do they localize, do they freeze, and so on? Now, if you go with universality, you will say, okay, I know the graphene problem, that's BD1, if I put this disorder, then I should get freezing, right? Okay, so let me just discuss the clean system to start with. So we use this unit cell, and you can see that I have colored the links by blue and red. So blue means the hopping amplitude is +1, and red means hopping amplitude is -1. So you can see that the flux through each plaquette is -1. And this, if you solve this tight binding model, it's fairly easy to do. You will see that there is a Dirac cone kind of structure that shows up at zero energy. So the low energy theory of this is a Dirac theory. Okay, and this is what I said: T square equal to +1 and a C square equal to 1. And there is chiral symmetry, sublattice symmetry as well. Okay, all right. So flux defect disorder. What do we do here? So what we're going to do is we're going to specify a concentration of these flux defects. Not only that. All this came after doing some calculations. We are also going to have disorder that is locally correlated. So what do we mean by this? So we can have monopole disorder. So that means that these zero flux plaquettes are uncorrelated. You can put them anywhere you want. Okay, and you do that by flipping the links on some Dirac string like this. Okay, you can have dipole correlated disorder. What I mean by that is I'm going to throw stuff like this on the lattice, but the average concentration will still be C. This being counted as 2 flux defects. Correct? And you can have tilted dipole, you can have quadrupole, you can have Greek cross, and so on. So now you may wonder, why am I doing all this, right? I mean, it's like, okay, so there are reasons for this. So first is, you can think of what is the low energy configuration of 2 flux defects. So what you can see is that if you think of these flux defects as some kind of spins, then there's like some RKKY like interaction between flux defects. And you will be able to see that if I put 2 flux defects, you can work this out. You will see that if they're neighboring to each other, then they will actually reduce energy. So there is a tendency in the system, even if you thermally excite random flux defect, to cluster. Okay. Then the question is, how do these affect physics? So I mean, I wanted to do something simple-minded. So I wanted to just say, okay, suppose there is some flux defect like this, then we know from BD1 symmetric class, etc. Any instance you have such in chiral classes, you have such local defects, they'll have 0 modes. So we could then try to see, okay, I have 0 modes, I could take the wave functions, try to find some effective tight binding just for them and try to understand some physics that way. Then we found something very interesting, that each of these things have different types of localized zero energy modes. So for example, this will have 1 over square root r, this will have 1 over r square, and the others will have 1 over r. They have different types of localized modes, zero modes around them. Okay, all right. So an important point is that the flux defects preserve the BD1 symmetry. Okay, so let me tell you the numerical results now. So transfer matrices. So if I look at the transfer matrix, you can see, just ignore these lines. I'll have something to say about that in a minute. These colors are for different types of flux, different types of defect correlations. You'll see that all of them are flat. What this is telling you is that you have a critical state. You have a scale-free state. That's what it is telling you. Okay. So these violet ones, they correspond to dipoles. So we have checked this not for very small concentration, but for very large concentrations. That if you go to much larger length scales and do some scaling, etc., you will see that they will also actually show critical behavior. Okay. So this is so the length scale associated with crossing over to this critical state is very large. Okay, so what you will find is, the first kind of surprising result is that this value, which is the limiting value, which we call chi, 1 by chi here, that depends on the type of defect correlations you have, the kind of the concentration of defects, etc. So you see this already, this supposed to be universal quantity, you are seeing that it is depending on details. Okay, so this is the statement. So now then we looked at conductivity. Okay. So if you find the conductivity at no disorder, the answer is 2 by pi, E square over H. So that is the result. So do people want to take a guess what happens to the conductivity when I put in this disorder? Increases, right? It increases, right? So it increases. The conductivity increases, and you can see that the way it increases, etc., is actually dependent on all of this details like concentration and all of this stuff. Okay, so important point is always larger than sigma 0. Okay, all right. So there is very strong dependence on defect clusters. Okay, what about multifractality? Okay, the honest answer is no. Right, but I'll have more to say. Yeah. Okay, so multifractality is the following. So you see, what we are claiming here is that there is termination multifractality. So by the way, we can do only this. These calculators are very expensive to get statistics, etc. So this is done only for the monopole configurations. So you can see that this sort of flattens out here like this, and we have checked that it flattens out by taking the derivative and showing that the derivative exponentially goes to 0. Okay, so it flattens out, and so it's termination multifractality. So the main message is that there is no freezing. Yeah, take 2 minutes. Yeah. Okay, so there is strong tendency towards termination behavior. So this is the result. So what are the lessons? We have critical states, we have conductivity which is always larger, and we have multifractality, which is showing tendency towards termination. So how do we understand this? So of course, the natural thing to do is to try to write down some field theory. So the field theory is you perturb the Dirac Hamiltonian with a set of disorder fields, right? So you can show that if you are in BD1 symmetric class, the only allowed disorder fields are this gauge fields and the mass terms, okay? These are the only allowed disorder fields in BD1 symmetric class. And now what you can do is, you can take the variance of this and variance of this M, and as was done in very early papers, the usual assumption is that these two are not correlated. And if you write down the RG equations for that, you will see that you will get something like this. So the mass term, the correlations of the mass does not flow, and the gauge term grows if I have any amount of mass term. And then there's a very beautiful paper that is this paper, which shows that when this quantity exceeds some critical value, then you get freezing. So what would be your guess? You check, you can go to our problem and find out whether this GMM is 0 or not. And we find that it's not 0, and it's quite big. So we should find freezing, but we don't find freezing. Okay? So what we did, we thought that this assumption of uncorrelated mass and gauge fields are is not correct. So we decided to also go to the numerics. We found out what are the correlations between this A and M. And we derived some new RG equations, including this, the correlations between J and M. I'm showing the most simplest version of this. The more complicated version of this has some 64 equations corresponding to all different possible correlations, etc. I mean, this is Hiranmaya at his best. I'm showing you the simplest ones. And there's a very interesting result that you find. If you start with everything very strongly correlated and almost equal, then you actually see that it'll evade freezing. Right? You'll see that all the G's will flow to 0. So it'll become almost Dirac equation-like. Okay? But if these are not different, for example, this is 95% of this, then you will see that on some length scale, it will look like it's not freezing. That's what is happening here. But on very large length scales, it flows off to frozen state. So point is that this again doesn't explain our numerics. So we don't have a theory of what's going on. So we decided to look at some stuff from our data itself. So this is what we find, okay? So what I'm plotting here is the conductivity and the sky. And remember, I have all different disorder realizations, different concentrations, different correlations of flux defects. They all fall on the same line, right? So there's some new universal state that is coming up where these two are connected in this way. The x-axis is the Lyapunov exponent at very large M system size. So once you go critical, the M by C, M is system size, C is that length scale, that will go to a constant. So that value, it's like an amplitude ratio. Okay. So I'm just making this point that they are following on all this. So we believe that there is a family of critical states here, right? And so now we can ask the question about density of states. So if you look at the density of states, you'll see that has some interesting feature. And the question is this some kind of Garde-Wegener? So here is where someone like Soumya, who is like absolutely top class numerics person, he was able to use this kernel polynomial method. And he was able to show that at least within the energy scales that we have probed, there is a power law in the density of states. It's not average. Yes. And so you'll see that this is it has some power law which goes like alpha rho, and alpha rho is negative here, right? And it depends on the concentration. So if you now look at the literature, you will see that this is very similar to what you will see if I had a pure gauge disorder in the Dirac equation. There, of course, alpha will be positive, but it's a power law. Okay? 2D. I mean, this is disorder averaged. Yeah. So the question is now I have power loss everywhere. So do I have some kind of conformal invariance? Right? And so what you can do is you can check whether your theory is conformally invariant. So if the theory is conformally invariant by looking at some primary operators mapping, etc., to the strip, by following this literature, you can show that this relationship has to be satisfied. So 1 by chi must be this, where alpha 0 is the derivative of my tau q with respect to q at q equal to 0. And this x rho is simply related to the density of states exponent. Okay? And this is the data that we have. And this is the calculated value of chi times this. It should be 1, and you can see that it is very close to 1. So, I mean, this is how much we can say. This is conformally invariant, is what we are claiming. Right? Okay, so let me summarize. I think, I'm run out of time. So the highlights is that Dirac fermions in Z2 gauge field background do not freeze, right? And you get this new class of critical states. So Mohit asked this question about why the conductivity goes up. So I have a very simple-minded answer for that. So if you make C equal to 1, that will be the 2D system with no flux at all. So, this interpolates smoothly between the E square over 2 pi, 2 by pi to some infinite value. So we have checked this. I don't have the I can show this offline, right? We have checked this. So it actually it does that. So it's like it wants to go to the clean tight binding model. So its conductivity goes up. I mean, this is the intuition. I don't have an intuition in terms of like some other way of thinking about it. Right? Okay. All right. So I have to make some other comments. So one of the referees asked us this question. So is this related to the BKT physics of the nonlinear sigma model? So what happens is the following. So if you make this claim that, okay, there is this chiral class and the conductivity will not flow there, then, I could just take a problem and take graphene and start removing links, right? So then at some point, I'll have some percolation transition to like localized states on these non-percolating systems, right? So that Gade-Wegener cannot be applied there directly, right? It's still in BD1 class. So what these authors argued is that you should, I talked about the phase of the nonlinear, the U term, the matrix nonlinear sigma model had an overall phase. You have to also think in terms of the BKT transition of that phase, right? So when you couple the sigma model and this BKT transition together, then you can recover some of those results, and those have been done in these series of papers. Okay. The point is, this is not that physics. Reason is that in this problem, you will find that the conductivity will always fall, right? Because you are removing links, etc. Whereas we are finding conductivity is increasing. Okay, so it does not arise from there. So maybe someone can help us understand what's going on. So thank you very much, TVRG, for all the inspiration over the many years. And I look forward to more inspiration from you in the coming years. Thank you.
Can I? Here. Just one question about random flux. If you have a small amount of random amplitude added on,
No.
Do those zero modes survive?
I didn't check that. I suppose they will survive.
Okay. And the second point is, part of your story sounds very familiar to what Lessig and Sambuddha and I talked about. But
Yes.
the point is that when you have these zero modes,
I cannot hear you, Kiran. Sorry.
when you have these zero modes, they induce a crossover from some non-universal power law regime. They create this non-universal power law regime, which then eventually crosses over to Gade-Wegener. So although it's always Gade-Wegener eventually, that eventually is of only theoretical interest if you can go to 10 to the minus 23 or something. What you see is a non-universal crossover. And that is what
So you think that is what's going on?
I think what you're seeing is the same thing. And again, this thing that everything falls on one line, we had checked that by putting vacancies with different kinds of correlations. And everything falls on one line if you plot versus the density of zero modes.
Sorry?
When you plot versus the density of zero modes, because that's the universal.
Okay, okay.
I think this is more or less the same
Okay,
thing.
we'll follow it up. Okay.
And it may just go away if you put some random amplitudes because they will destroy your zero modes.
Hello. Hi. I wanted to give some intuition behind why the conductivity increases with disorder. This is a problem we have also looked at in the Kitaev model. And what we find is that the chiral spin liquid is basically the P plus IP superconducting phase. So when you put these fluxes, they can bind a Majorana, and with increasing density of fluxes, which is increasing disorder, you can get tunneling between these Majorana modes, which leads to this enhanced conductivity.
Yeah, I mean, that's the sort of zero mode stuff.
Yeah. So we have looked at
understood.
that, and
We'll
the same behavior comes out, giving you this Majorana metal.
So, hi. Yeah. So I have a very naive question that if you really make vacancies at the graphene, there are dangling bonds, and people have found the local moment getting formed there. So if you really have such a thing, local moment form, then all the time reversal symmetry and etc. you're talking about.
Fair enough. Yeah, no, that's a fair question. But for that you need some interactions and so on to form moments, etc.
Yes.
This is just a non-interacting tight binding model.
Yeah, but that will in reality be the
Very much, yes. So maybe Kedar, if you want to add something to that.
there is. Sorry. Yeah. Yes. But experimentally, people have actually found. I see.
Yeah, so maybe a question both for you and Kedar.
Question for Kedar. Yes, please.
So this, so in terms of the Dirac operator with random gauge field and random mass, that's related to a classical StatMech problem, 2D XY model without vortices in a random field.
Yes, yeah.
So the new results that you're all finding, what in that language, what are the conclusions?
I don't speak that language, so I don't know. So maybe Kedar, you can.
This is ancient.
Yeah.
Okay.
So this is a gross nebu being related to some other problem, right?
No, it's this so-called cardio-Sloan model.
Okay. Yeah, sorry. Shabari.
Any other question? If not, okay, I have a question for you. Did you look at the typical density
I
states?
don't think we did, but we haven't looked at it. No. Average density state.
Do you know what? So generally, like for localization, you use typical density of state as an order parameter. But for Anderson localization, but for this freezing and termination, what happens to typical density of state?
I don't know the answer. We have not looked at it. We have looked at the results that I showed. We looked at the statistics of the wave functions. Yeah, density of states is very difficult to calculate. Right? That's
yeah.
Yeah, hello. Something to say that is the freezing and localized that you told. The localized is the decaying and pull up, and freezing is the constant.
No, freezing is not constant. Freezing is the wave function is spread out, but it has those statistical properties where this tau q will do something like this. So tau q will do something like this. So if your two dimension starts at -2, it goes up, and this is q. So it reaches when q equal to sorry, when Q equal to 1, it will reach 0 and then it will remain 0. This is what is we call freezing.
Okay, and also the archiveability of reference that you have given, that is the RG that you shown.
Yes.
That has been mentioned
Yes,
on this
yes.
archive. And also something to say, just to show on slides, conformal invariant. I am working on the conformal
Yeah.
field theory published paper. So when you go to the conformal field theory, there is the main part of the conformal field theory about the conventional.
I
field
think
theory.
in interest of time, we will close this session. Let's thank Vijay for a very interesting talk. You can please go ahead and have a discussion with him later on.